All right, so we're going to pick up day 2 now of the unit 4.1, and we're going to talk about how to graph polynomial functions. Now, yesterday we did monomial functions. Today we're doing polynomial. Polynomials are a polynomial in one variable is an expression of the form where you have some coefficient times x to a power plus a different coefficient times x to a lesser power plus a different coefficient times x to a lesser power times, and that can go on and on and on and on. Eventually, you get to a coefficient times x squared plus a coefficient times x plus a constant. Now, of course, there can be gaps. We don't have to have, if we had a x to the fourth term, we don't have to have an x to the third. We could have like an x squared next or just an x next. But here's the important things. All of the coefficients, the leading coefficient cannot be 0, especially for the first term. The leading coefficient can't be 0, and we have to make sure that all of our integers are not negative. All of our exponents are not negative. So, because the terms are written in order from greatest to least, this polynomial is written in what we call standard form. So, standard form is the greatest degree first, followed by the next highest, followed by the next highest, so on and so forth until we get down to constants at the last spot. All right. The degree of the polynomial is n, and the leading coefficient is a sub n. So the degree is the leading coefficient exponent, so in other words, the highest exponent, and the leading coefficient is that first coefficient. So if we look at this table here I made here, so a constant function, like an example would be 17. Of course, there is no x term there, so it's to the 0 degree, and its leading coefficient would just be 17. Linear functions, 3x minus 4, that is the first degree, and the leading coefficient there is 3. Quadratic, the degree is 2, and the leading coefficient of this quadratic is 8. Cubic functions, leading coefficient is 3, and the leading coefficient of this cubic function is 2. Quartic functions are to the degree of 4, and this leading coefficient is negative 6. And quintic functions, the degree is 5, and this quintic function is to the degree of 12. So that is how different polynomials are named. It's after the degree of its highest power, up to 5. After quintic functions, we really just say functions with a degree of 6 or a degree of 7 or so on and so forth. All right, so as we look at these down here at the bottom of the page, we're going to just kind of continue what we were just doing, degrees and leading coefficients. So you'll see that this first polynomial is in standard form, so we can look just at this first term, the 2x to the fourth, and that tells us our degree is 4 and our leading coefficient is 2. All right, and so then if you look at b, again, we just look at the 7x cubed. The degree is the exponent 3 and the leading coefficient is 7. Now, for letter C, that is not a polynomial in one variable because there's x's and y's. So we would say not a polynomial in one variable. All right, so then the next one, x to the fifth is our leading term, and that is in standard form, so that is the correct leading term. So the degree is 5, and the leading coefficient is not x. Please never put x as a leading coefficient. Leading coefficient is 1. All right. So let's look at how this plays out. The density of the sun in grams per centimeter cubed expressed as a percent of the distance from the core of the sun to its surface can be modeled by this function. F of x equals 519x to the fourth minus 1630x cubed plus 1844x squared minus 889x plus 155. That's a mouthful, where x represents the percent as a decimal. So at the core, x is 0, and at the surface, x is 1. So if we think about percent as a decimal, we just move the decimal place over 2 spots, so 10% would be like 0.1, 20% would be like 0.2, so on and so forth. So the core density of the sun at a radius 60% of the way from the surface, we would change the 60% to 0.6. So in order to find the core density at 60% away from the core, we would just plug in 519 times 0.6 raised to the 4th minus 1630 times 0.6 raised to the 3rd plus 1844 times 0.6 squared minus 889 times 0.6 plus 155. All right. So I did some quick math here and came up with 67.2624 minus 352.08 plus 663.84 minus 533.4 plus 155. And now if I add all of those things together, it comes out to equal 0.6224. Now, what we're going to do with that 0.6224 is plug that in to right next to the 0.6 spot. All right, and now we're going to do the same thing over and over again with the table. So go ahead and pause the video and fill out the table. Just repeat these steps over and over again for each x value. So start with 0.1, go all the way up to 1. So now that we have the table filled in, we would be able to graph, and we can kind of check our table versus the graph that's already been provided to us. You can see that at 0.1, they have a point that is about a fourth of the way between 80 and 90 on the graph there, so that'd be about 82.9619. And then the next block at 0.2, there is one that's almost to the 40 mark, so that'd be the 38.7504. And you can see this mapped or graphed out the rest of the way. So that's how you build a graph of a polynomial function. You just got to make a table, find some x values. It doesn't matter which ones you pick. Usually you want to think about the context of the situation. That's going to help you the most if your situation is like a real world situation. Obviously, we don't care about what happens when we have a negative x, because there's no way to have a negative percent of this polynomial. And we obviously don't care about what happens when our x is bigger than 1, because if it's bigger than 1, then it's outside of the sun itself, and so that doesn't fit our context either. So we just care about those numbers between 0 and 1. So that's why we graphed those numbers that we did. So in real-world scenarios, think about the context. That's going to help you pick which x values to use for your table. If it's not a real-world scenario, you're just graphing a polynomial, just kind of in math class, then just pick x values around 0. Like maybe go from -4 to +4. And if that doesn't help you all the way, then you might go a little further left or right. But that should be a good start to give you a good idea of what your polynomial is going to look like. All right, well, if you have any questions, please shoot me an email or a Canvas message, and I'll get back to you as soon as I can. Hope you have a great day. See you later.